Hi everyone, I'm Dr. Laili from University Malaya. Today's presentation I will focus on how we're going to utilize natural energy in this content is sunlight to mitigate or degrade the persistent pollutants from the industries in order not only to generate a sustainable ecosystem but also give a positive impact on the environment, humanity and socials. The title of today's presentation is the titanium oxide, zinc oxide supported chitosan, photocatalyst to the absorption and photodegradation process of the synthetic dye. And together with me to develop this project is Mr. Azam and also Prof. Rafi. So enjoy the presentations. Wastewater from the dye is the huge pollutant around the world. Some dye doesn't even degrade in water. Others that do degrade produce the harmful substance as they are decomposed. Additives used during the dye process include the harmful substance, including acid and alkalis. The question here is, are the synthetic dye harmful to environments? Synthetic dye have the harmful effects on the environments and human beings. Exposed to the large doses of this substance can be toxic and can have several effects in the human bodies. Water pollutants can also result from the manufacturing synthetic dye when the untreated dye is dumped directly on the bodies of water. In conjunction of the 2018 edition of the United Nations World Water Development Report stated that nearly 8 billion people will suffer from the clean water by 2050. This is the result of increasing demand of water, reduction of the water resources, and increasing pollutant of water, driven by the dramatic populations and the economic growth. Conventional approach, including biological, chemical, physical methods, have not been achieved the complete degradation of the organic pollutants. Besides, it also requires a long operation times and procedure secondary, and it have a possibility to produce a secondary pollutants, which is increase the cost of the process. Since its emergence, the advanced oxidation process, or we known as the AOPs, have gained a great deal of interest in the wastewater treatments and recycling technologies. Relative to the traditional methods, these AOP are efficient in treating the wastewater to degrade a wide variety of the organic pollutants. The problem faced by the treatment of processes such as sludge developments, the formation of the secondary contaminants, high cost, and the incomplete degradation of the organic pollutant render the AOP more effective technologies. Photocatalysis process belong to the advanced oxidation technology for removal of the persistent organic pollutants and the microorganisms from water. The photocatalyst is a process in which the light energy is used to derive the pair of the chemical reactions. Due to their activated stage, the electron in the hole perform chemical reductions and the oxidation as through they were highly reactive reagents in the chemical reactions. Photocatalysis process belong to the advanced oxidation technology for removal of the persistent organic pollutants and the microorganisms from water. The photocatalyst is a process in which the light energy is used to derive the pair of the chemical reactions. Due to their activated stage, the electron in the hole perform chemical reductions and the oxidation as through they were highly reactive reagents in the chemical reactions. Several numbers of the metal oxide catalysts, just as the titanium oxide, zinc oxide, or strontium oxide, have been applied or tried for the photocatalytic water degradations. Among these catalysts, titanium oxide have been demonstrated to be an excellent catalyst in photodegradation of the organic pollutants due to the effective non-toxic, low-cost, photostable, cost-effective functional materials, and can be reused. It means that we can recycle it. Titanium oxide generally is considered as the best photocatalyst and could detoxification water from the several organic pollutants. In addition, titanium oxide have the large surface area that can facilitate the fast rate of the surface reactions, which has attained considerable attention due to its distinctive application as the photocatalyst. However, there are still limitations of the titanium oxide as a catalyst, and is still far from becoming a potential candidate in the environmental treatments, water treatments. The efficient use of the visible light from our sunlight and improvement of the photocatalytic activities are the two important issues must be addressed to meet the economical viable on the large-scale environmental remediations. Therefore, the high photocatalytic activities of the titanium oxide photocatalyst could be achieved with the suitable architecture that minimize the recombination of the photo-induced electron-hole pair by quickly separate them before the electron-hole pair lost their energy in the form of the heat and photon through the recombination process. Furthermore, the titanium oxide could not use satisfactorily due to its poor separation ability from the suspensions and flowability. Titanium nanoparticle-based photocatalysts has demonstrated a promising dye photodegradation efficiency up to 95 to 97% under the UV irradiations. In order to enhance its light sensitivity under the solar irradiations, coupled with the zinc oxide has been proposed here. Zinc oxide is a promising semiconductor photocatalyst on the count of its wide band gap. Is it 3.7 eV, low cost, non-toxicity, and a good oxidizing power. On the other hand, electron-hole recombination is the major impedance to the widespread application of its photocatalytic activities. Compared to the titanium oxide, zinc oxide can absorb a large portion of the UV spectrum and show a superior photocatalytic properties. However, the photocatalytic capabilities of the zinc oxide are limited by the wavelength of the UV light, and it cannot absorb the wavelength of the UV light. Some problems remain to be resolved in its application, just as the rapid recombination of the photon-generated electron-hole pair, and improving the photocatalytic activity of the zinc oxide has therefore become a hot topic for researchers in the recent years. One approach is to combine zinc oxide with other materials to form a hybrid photocatalytic system, thereby can improve the separation of the photon-generated electron-hole pair. Zinc oxide is a promising semiconductor photocatalyst on the count of its wide band gap. Is it 3.7 eV, low cost, non-toxicity, and a good oxidizing power. On the other hand, electron-hole recombination is the major impedance to the widespread application of its photocatalytic activities. Compared to the titanium oxide, zinc oxide can absorb a large portion of the UV spectrum and show a superior photocatalytic properties. However, the photocatalytic capabilities of the zinc oxide are limited by the wavelength of the UV light, and it cannot absorb the wavelength of the UV light. Some problems remain to be resolved in its application, just as the rapid recombination of the photon-generated electron-hole pair, and improving the photocatalytic activity of the zinc oxide has therefore become a hot topic for researchers in the recent years. One approach is to combine zinc oxide with other materials to form a hybrid photocatalytic system, thereby can improve the separation of the photon-generated electron-hole pair. To solve this problem, chitosan-based particle composite have been studied increasingly as an alternative adsorbent in the water treatments, just as using the metals, metal oxide, and bimetallics. Furthermore, chitosan can act as the coagulating or flocculating agents to remove several types of pollutants, including organic compounds, metal, and other from the contaminated water. It also been already used in the organic matter removal for the wastewater, especially those resulting from the food processing, being very effective in reducing reducing the oxygen chemical demands. It is well known that application of the photocatalyst, just as from the metal oxide, titanium oxide, and zinc oxide, is limited by the actual facts that UV activation is required. The bandgap energy is about 3.2 eV, and this implies that lower than 5% of the solar spectrum has sufficient energy to activate the photocatalyst, and by the fast recombination rates of the electron-hole pair generated. Hence, modification of the photocatalyst through the metal or non-metal doping of their recombination or with the other semiconductors are the common methods used to improve the photocatalytic performance and for the activation by the visible light irradiations. Therefore, zinc oxide was combined here to endow the titanium oxide nanoparticle with enhanced absorptions of the visible radiations, thus can improve its photocatalytic activities. It also been reported that the heterogeneous photocatalytic reactions will be performed at the surface rather than the solution box, and the surface properties of the titanium oxide are critical for the efficiency. Per absorption on the surface of the titanium oxide particle is required for the efficient photocatalytic degradation of the dye, and more significant absorption enhance the rates. This approach target the use of the supported materials such as microporous solide, zeolites, mordanite, activated carbon, alumina, silica, microporous silica on the surface. Hence, most of the photocatalytic activities were enhanced in these contents. And here, chitosan is used as a support material due to the presence of the amino and hydroxy group, which serve as the active site capable for enhancing the absorption properties of the hybrid catalyst. The particle size, morphology, nanoscale photocatalysts are also a problem in the full-scale water and wastewater treatment because the particle should be removed or recovered after the treatments. To address this problem, chitosan-based particle composite have been produced in the microbits, which can be filtered out by the simple filtration process at the end of the treatments. The immobilization of the catalyst has brought increasing the interest to the study of the polymer-based composite, whose porosity and the pore size can be controlled. These research provide a simple and readily accessible route to the formation of the ternary titanium oxide, zinc oxide, and chitosan, which overcome the charge recommendations and separation limitations of the native titanium oxides. The modification allows the titanium oxide to be a photocatalytic under the visible light sources. And chitosan is sensitive to the various types of the photooxidation of the UV light. The chemical structure of the chitosan change due to the cleavage of the glycosidic bonds and the formation of the new carbonic groups in the chitosan oligomers. When a colored organic compound is present, it acts as the photosynthesizer and have a capability of injections and electrons into the conduction bands of the semiconductor particles to generate an oxidation process. The oxidized form of the dye molecule is further degrades. Through a simple mixing method, these ternary systems can be produced by the exitose process and have relatively high absorption capacities, but once water treatment is treated, the catalyst can be reused effectively. This methodology has provided more sustainable treatment process than the other approach. To solve this problem, chitosan-based particle composites have been studied increasingly as an alternative adsorbent in the water treatments, just as using the metals, metal oxide, and bimetallics. Furthermore, chitosan can act as the coagulating or flocculating agents to remove several types of pollutants, including organic compounds, metal, and other from the contaminated water. It also been already used in the organic matter removal for the wastewater, especially those resulting from the food processing, being very effective in reducing the oxygen chemical demands. The hybrid system have been performed using the simple acetyl process with the acetic acid as the medium. Then the obtained photocatalyst has been characterized in terms of its surface and the structural properties. Before it being proceed with the photocatalytic analysis under the visible regions using the methylene blue as the model of synthetic dye pollutants. The surface morphology analysis of the hybrid catalyst was performed to investigate the dispersions of the zinc oxide and titanium oxide over the supported chitosan with the field immersion scanning electron microscope (FEM. The image demonstrates that non-spherical shapes but with the macroporosity structure has been observed. The porous structure is attributed due to the presence of the chitosan macromolecule, which can be further assessed as the absorption site during the dye treatment. Characterizations using the Fourier transform infrared F-type spectroscopy analysis provide information regarding the active surface and the functional group of these hybrid systems. The FTIR spectrum of the chitosan exhibit the absorption bands at 3447 and 1651, which is attributed to the primary amine and hydroxyl functional groups. The FTIR spectrum of titanium oxide exhibit a broad absorption bands at 3441, which confirm the OH stretching vibration of the adsorbent water on the TiO2 surface. The peak at 499 show the distinct stretching vibration of the TiO2. The band of the TiO2 chitosans means that the connection band of the TiO2 and chitosan reveal the integral characteristics for both chitosan and titanium oxides. The strong peak at 3441 is shifted to the lower wavelength, which correspond to the stretching vibration of the hydroxyl and the primary amine group, and become border indicate some interactions between this group and the titanium oxide. The peak at range of 1000 to 1600 are ascribed as the bending vibration of the primary amines and stretching of the carbonic groups. The intensity of this peak in the titanium and chitosans has been attributed to the less available of the free hydroxyl and primary amine group of chitosans and their respective involvements in the bonding with the TiO2. And these groups serve to coordinate and reaction site for the absorption of the organic compounds. Furthermore, the peak at the 400 to 900 refer to the OTiO2 bonds that prove the combination of the TiO2 and the chitosan matrix. Therefore, the stretching vibration of the hydroxyls and the primary attract the involvement of the functional group present on the surface of the TiO2 and chitosans during the methyl blue absorption process. In order to examine or to demonstrate the post-structure nature of this hybrid system, the BET gas absorption measurement has been carried out. And on the other hand, the nitrogen absorption desorption isotherm curve of the hybrid system has been also calculated and showing that this type of the hybrid systems correspond to the type 7 isotherms in the binary classifications, and showing that it's a typical mesoporous materials. According to the IUPAC classifications, the hysteresis loop belongs to the type H3, which shows a parallel plate split pore structures. Then the pore size distributions of all samples, which calculated from the desorption branch of the nitrogen absorptions via the Barrett-Janer-Helander methods, the pore diameter of the chitosans of this hybrid system were found to be in range of 29 to 11 nanometers respectively, which has further confirms that all samples were in the mesoporous regions, which is the mesoporous region which is in the 2 to 50 nanometer. The mesoporous structure is important here for the interactive and the absorption sites of the catalyst during the treatment process. For the crystallinity analysis, it shows that the anatase phase is predominant for the hybrid systems. The SRDP of the pure TiO2 and zinc oxide also become significant or visible in the hybrid system, and this confirms that the both of the metal, which is the TiO2 and zinc oxide, were present in the crystalline state of all the samples. The result were also consistent with the what was found in the literatures and suggested that some change occur due to the hydrogen bonding with the chitosan group. In order to study the light sensitivity of this catalyst, the UVDR spectra analysis has been carried out, and it shows that the band gap found for all the samples were calculated to be in range of 2.75 to 2.49. This result proved that chitosan has lowered the band gap in the gradual trends of the titanium oxide and zinc oxides. And it can conclude that the chitosan induced a band gap narrowing in this system, which result in the use of prepared composite for the photocatalytic removal of the methylene blue dye under the visible irradiations to generate more electron-hole pair and give a maximum visible light harvesting. The photocatalytic degradations of the methylene blue was observed for the 60 minutes and 50 minutes as a time interval. Visible spectroscopy was used to measure the rate of decrease in the methylene blue. The result of measurement has shown as the percentage of degradations and the rate of the degradations. The percentage of the photodegradation result, the rate of constant for the photodegradation result for the sample with the different compositions. For this, we have verified the different compositions of the ternary elements, Ti2, chitosan, and zinc oxides. And it can be seen that the sample with the ratio of 1 to 1, which is the ratio of the TiO2, zinc oxide to the chitosan, have the highest percentage of the photodegradations out of all the samples. The sample show the high rate of constant photodegradations. Based on the results, it shows that only 10% of the zinc oxide shows the best performance due to the zinc oxide photosensitivity, which influence the degradation of the pollutant itself. And in terms of the effect of the pH, the effect of the pH value of the methylene blue on the percentage of the color removal efficiency has been carried out. At the pH 3, the efficiency of the catalyst reported the lowest percentage, which is at the 96% due to the high acidity stage of the pollutants. Meanwhile, at the pH 5, the percentage of the degradation was recorded 2% higher than the pH 3 due to its lower acidity, which separate the molecule at the much slower rates. For pH 7 and 9, the percentage of degradation were increased up to 75% and 78% respectively. Meanwhile, at the pH 12, the reported of the highest level degradation, which is the 77%, due to the low pH, which more hydrogen ions are available to protonate the amino group of the chitosans. Since chitosan was not cross-linked, it reported a lower absorption at the pH 3 for the methylene blue. At the highest pH, the increasing number of negative charge sites on the adsorbent have led to the strong absorptions, and whereby that's why in the results that higher photodegradations has been occur at the higher pH medium. As a conclusion, for this study, we have successfully produced the ternary system of the photocatalyst with a different composition ratios, and it shows that the composition of 1 to 1 shows a optimized results in terms of the homogeneity, light sensitivity, and crystallinity. And considering the characterization result, the information of the core, its integrity surface appear to have the irregular pores. Band gap narrowing from the 2.9 to 2.6, and it makes sure that this photocatalytic system exhibit a good performance in the visible regions. Chitosans act as a binders to bind the Ti2 and zinc oxides and assist for the absorption of the zinc oxide as the photo dissolution inhibitor. Also, the furthest of the hybrid catalyst inhibit resolve the recycling issues that has been associated to the TiO2 system. In summary, the combination of these three elements provide a facial routes for the treatment of water treatment by maximizing the efficiency with it can be retreated and recycled. The photocatalytic activities of these systems exhibit up to the photo efficiency up to a 84 to 90% degradations of methylene blue within 60 minutes of radiations. Thank you. This study has resulted 4 published ISI paper together with 4 winnings medal awards in the exhibitions, international and national levels. Thank you everyone, and I hope that this sharing session will provide a new insight, especially in water treatment system with the sustainable approach. Thank you for your time and thank you for your attention.